Okay, welcome students to video class number 10, and in this also we are going to deal with the signal flow graph, and I named it as part 2. Here is a question for you, a block diagram, and which I asked you for a homework, and you were asked to prove that the transfer function is g1 g2 plus g1 g3 divided by 1 plus g2 plus g3 plus g1 g2 h1, and you have proved this by using block reduction techniques, and I think you were having about 4 to 5 steps to arrive at this. Now the same question is been again asked, but you are to obtain SFG and then find the transfer function from the given SFG using Mason's gain formula. Okay, so it is always obvious. I mean, in the question, it is not necessary to mention about this Mason's gain formula. You need to apply this. Otherwise, if you want to use back substitution method, then the question will be specified like that. Otherwise, always use Mason's gain formula for evaluating transfer function from SFG. Okay, right? Okay, now let us, first of all, the first step is to construct the SFG. What is SFG from this? Now, as I told you, so this is your R of S and this one is your C of S. So anyway, you can have this node marked, that is the input and the output can be marked as a node, as I told you earlier. So this is R of S and C of S. Then after the R of S, you have a summer that can be replaced by a node, and join those nodes. Then you have a G1 between two summers, right? So you have another summer, so you can represent that by another node, and draw a line connecting these two nodes, and over the node you may write this as G1. And then you have say you have a no, you have a takeoff point, and after this point you can say, let us consider this one as a separate node. Okay, so that is this takeoff point. Now between this takeoff point and this summer you have a transmittance G2, and after that you have a summer. Okay, now then you are connecting to this. Okay, so this is it. Now now look at this. So from before G2, that is G2, you have one more path, that G3 comes ends at or terminates at this node, right? So it starts from G2 and terminates at what? Terminates at this node. Now from G2, from the G2 you have one more node which is going to this node, right? So that is to the summer. That is, the summer is represented by this node. So you can have this, but what about the sign? The sign is minus, so that means you can represent that as minus h1. Then one more loop is there that comes from this, right? Okay, so and that will reach at this summing point before G2. So that means you can represent the same like this. So you don't have, mind you that this branch and this branch doesn't have any connection. Okay, so this is it. Now you can represent that as -1 because that's a unity feedbacks. Now, okay, so this is your SFG, right? Now let us have the transfer function using gain Mason's gain formula, and that is given by, the transfer function is given by pk into delta k by delta sigma k. Now the first objective is to find out the k. That's it. How many k's are there? So just allow a signal to pass from R of S. So it will go in this direction and will reach z of s, right? Without any sort of repetition. That's one path. Now, if you have a closer look, you can have a signal also going in this direction as well. Okay, so that means there are two paths. So that results in two path transmittance. Say, call this as P1 and P2. The first path, which is identified, the transmittance is identified as the product of G1 and G2. So that is G1, G2. Then you can have another, that is G1, G3. That is P2 is equal to G1, G3. That is the second forward path. Now coming to the loops, how to find out the loops? Say, call that as first loop as L1. Start from this point. Allow a signal to pass through this and see the paths by which the signal moves and come back to this point. That is what is called as a loop. So if you have a closer look, you can see that a signal goes in this direction and it can come over here. So the transmittance is the product of that path, right? So this will be the product of the transmittance of the path through which the signal goes to complete a loop. So this will be G1, G2 and minus H1. So this will be minus G1, G2, H1. Now let us go for the another. Is there any? Okay, let us look at like this. So it can also go in this way, right? In this way, and it may reach here, but that is not a loop. If a signal starts from here, that should reach here. So this is not a loop, right? Now you can also think of having like this. This is also not loop. Why? Because the signal that is sent over here is not reaching at this point. So you cannot consider that as a loop. Now move to the next point. Again, pass a signal through this. That means you can have a path like this, right? Minus G3. That is the same signal which is allowed to go through this will reach here in this path. That is G3 minus G3, right? So that is another loop. Now again, you can have one more loop like this, right? A signal that can also go in this direction and reach here. So this will be minus, so L3 is equal to minus G2, right? Now, what about delta 1 and delta 2? Now, delta 1 and delta 2. Now, how will you find out delta k? Delta k is the graph determinant when that kth path is taken away from this. Now, let us try to take away G1, G2. Now, when you take G1 and G2, all these knots these knots will be removed from this graph, meaning none of these loops are separate from these knots. So that is, all these loops are some way or other connected to all of these knots. That means these knots are dependent on path 1, right? These loops are dependent on path 1, P1. So when P1 is removed, there will be no loops, right? No loops independent of P1. Similarly, you can, by observation, you can see that P2 also forms, P2 is also common to, that is the P2 transmittance is common to, right? Okay, so look at this. Say you may feel that L3, what is a problem with L3? That is minus, L3, that is minus G2. Minus G2 is this loop, right? Now the path is G1, G3. When you take away this, actually this knot is removed. That means this loop is also affected. So there are no loops which are independent of this loop, independent of this path. Okay, so this will be 1, this is also 1. Now I'll just give you another illustration where you can have an independent paths, right? Say, for example, if you have a signal flow graph like this, right? Okay, now look at the scenario. So this is actually a path, right? So call this as A, B, C, and D. Okay, so this is one path, right? One that you may call that as Z, and the loop is CD. But when you write the delta 1 of or delta k of this path, this will be 1 minus AB. Why? This AB is a loop which is totally independent of this path. If you remove this also, you can have this loop. Okay, in that situation, this delta 1 and delta 2 will be having a value. Otherwise, it will be always equal to 1. Now, what is your delta? How to find out delta? Delta is nothing but it is 1 minus, right? 1 minus the sum of the loops. So the sum of the loops is minus G1. Okay, so this is minus G1, G2, H1 minus G3 minus G2. Now, plus, what's the next step? The sum of the product of the loops taken two at a time. And the importance of that loops is they have to be non-touching. And from the figure, you can see that none of the loops that we have found out or we have identified are non-touching loops. They are touching in some way or other. They are touching to each other. Look at this: G1, G2, H1, right? G1, G2, H1. It is having a common point with minus G3 as well, right? So it is also having a common point with minus G2. So all these loops are touching loops. So the rest value will be equal to 0, right? So that your delta becomes 1 plus G1, G2, H1 plus G3 plus G2. Okay. Now take all these things and put into this equation. That is, a transfer function is given by P1 plus P2, right? P1 into, it will be P1 delta 1 plus P2 delta 2 by delta. So substituting in that, you will get this as G1 G2. G1 G2 into 1 plus G1 G3 into 1 divided by 1 plus G2 plus G3 plus G1 G2 H1. Okay, so you got the same transfer function as this. Now just look at your work which you have done as a homework, how many steps you took, and it is a lengthy process as well, right? Now it is, look at how much easy it is. It is just the only thing that you need to see is you need to identify the paths, the forward paths as well as loops, right? Once if you found out this correctly, then it is quite simple. It will take only a few minutes to arrive at the transfer function. Now when you practice this method a lot, you can simply, by seeing the signal flow graph itself, without doing this, you can simply uh, tell the transfer function from the figure itself. Okay, so that's it. Okay, now there is a mistake in the just in the figure. It's not like this. You will have to take this from this. Okay, and our problem with the signal flow graph. So this is your next question. So I call this as question 2. This one as question 1. Now this is a bit complicated block diagram. As far as SFG is concerned, it's simple. Now let us see. Let us first of all draw this. I'm going to introduce just to explain what the block diagram is. You have three summers, okay, and this is G1, G2, G3, and you have an H1, H2. Okay, now let us try to draw the SFG. Now, as I told you, SFG always starts when this is your R of S and this is C of S. And the question is, as usual, find out the transfer function from the SFG. Okay, from SFG. Now, in this case, you need to be very careful when you draw the SFG. So it starts from SFG as always, and you can represent this by a node. Then you have a G1 coming over here. So I told you, then you have a summer, right? So it's always nice. I recommend that wherever the signal changes, put those. So this is a takeoff point. This one is a summer point. You can represent the takeoff point and summing point as a knot. So no problem in doing like this. Okay. Now, after that you have one more takeoff point, and this has to be definitely, this has to be these two knots. This has to be represented by two separate knots. So then after that you have a summer, right? Okay. Now, this summing point and this one are the same, because at the summing point you are going to get the two inputs, and here also you are getting the same signal. So no problem in associating these two knots, but you cannot do this because of the two different signals. Okay. Now, okay, now finally at the CS. So this is CS and this one is RS. Okay. Now let us label these things. Say this one is a summer, and this one will be your G1, right? This one is your G1, right? Then after that you have this point. Okay, then you have a summer. After the summer you have a G2. Then you have this takeoff point. Again you have a summer. Okay. Now coming to this point, you can just have a, say, look at this path. After G1 you have a, this is your G1, and this point corresponds to this. So from this you have another branch, and that comes over here. So this one represents the summer, so comes over here, right? So mind you that always put arrow, don't forget to put arrows. So this is your G3, right? Now what all things are to be done again? Say, look at this. After G2, that is this knot, and from this G2 you have an H1. Okay, so you have an H1. So this is your H1, and that is a minus H1. Put minus H1, and it is coming to this side. So you can draw like this, right? Then after that you can see an output is taken from this point, that is from CS, or you can consider this point, because I told you this node, this point is a point where you are having the signal that comes from G3 as well as G2, and the same signal is fed back, so you can consider this as a node. So that means you can take this from this, and where it gets terminated, it's terminated at this sum just before G2, that is this point, right? So this is it, and you can represent that as minus H2. Okay. Right. Okay, now let us let us find out the for paths, the number of paths. So what is K? You know, as always, the equation is sigma K is equal to Pk delta K by delta. Now we have to find out the value of K. K is actually equal to 2, right? K is equal to 2. So this one is one path, that is G1, G2. Another path is G1, G3. So what will be your corresponding P1 and P2? P1 and P2 will be, P1 is G1, G2. That is the forward path transmittance, overall forward path transmittance of path 1. And the overall transmittance of path 2 is G1, G3. Okay, G1, G3. What you can call for delta 1 and delta 2? See, we'll come to that after finding out the loops. That will be nice. Okay, now what are the loops? Let us see how many loops are there. So my intuition is I know that this has 3 loops. Let us see what are those loops. Let's start from here. Say a signal is passed, and this is a way by which a signal can come to this point, right? So one L1 will be, and so the L1 will be equal to, the loop transmittance will be G1, G2, G1, G2 into H1, but with a minus sign, right? G1, G2 into minus H1. Now let us see another, is there any other possibilities from this node? A node signal travels in this way, and it comes over here. It's not coming over here. So this is not a loop. What about this? Is there any provision to reach here? No. Okay, so you can leave this node and come to this node, and allow a signal to pass through this. Is there any provision to get the signal? See, G3, okay, and it comes over here, and okay, minus H2, and that's not coming over here. Okay, now this is why I told you that you should represent this and this as this point and this point as two dots. The reason is, here the signal is a different signal. Here, when it comes over here, you are having a different. So wherever the signal changes, you can put that as a knot. See, if it had it been the same knot, what would have happened? There would have been a loop, right? So that, yeah, a signal that comes over here and can come over here. But since these two nodes are different, you cannot say that a signal passes through this point will reach over here. Okay, so these two are two different points. So hence there is no chance of a loop over here there. Now what about this? See, there can be a possibility like this. Look at this. G3 minus H2, then G2 over here, right? Right? Look at this. So this is how. No, nowhere, just be careful. Nowhere the signal gets repeated on any of the paths, right? Okay, so I'll just write it for you. You may just look. G1, G3, then that signal comes over here, H2. I'll put that minus later. Then you have a G2. Then you have a H1, right? Okay, now you have two minuses and those minuses gets positive. Now what about the third one? Now you have got any third one, okay, you have a third one as well. So look at this, G1, G2, H1, okay. Then another one is there, that is coming at this knot. This is a loop, G2, H2 or minus G2, H2. Now coming to delta 1 and delta 2, what must be this? None of the loops is independent of P1 and P2. That means delta 1 and delta 2 is equal to 1. Now what about delta? Delta is, okay, what about delta? Delta is 1 minus the sum of the individual loops. So this will be 1 minus G1, G2, H1 plus G1, G2, G3, H2, H1 minus G2, H2. And from the figure itself, it is very clear that none of the loops are non-touching loops. So the rest of the terms becomes equal to 0. So now putting all these things in this equation, we'll get the transfer function to be P1 delta 1 plus P2 delta 2 divided by delta, or this is equal to G1 G2 plus G1 G3 divided by 1 plus minus 1 plus G1 G2 H1 1 plus G2 H2, then you have a minus, that is G1 G2 G3 H2 and H1. Okay, so you must be very careful about this. What we learned today is, from this signal flow graph is, you need to represent each points of different signals by different nodes. There's the point at which the signals are different are to be represented by different nodes, as in this example, right? These two nodes. So here you have a signal, you have a different signal. So we are representing those as two nodes. Now, had it been the same node, you will be getting some other loop as well. So which is not true. Anyway, so how will you understand that that's not true? So, no, do you have any surety that this is your transfer function? How will you prove that this is the transfer function of this block diagram? Okay, you can also have a block reduction technique, right? Block reduction technique, and I am giving you this as a homework to do, and I'm sure that you may not be able to arrive at this. There are some complications in this. This is a bit tough in terms of block reduction technique. Now, what you need to do is, first of all, you can bring this point to this. By bringing this, you just need to add one G2 here, G2 H1. Then, after that, you can see that you don't have any other provision, just to think of splitting the summer in a peculiar way, so that our objective is either to convert this block into a canonical form or a parallel form, whatever it is. So just think of a situation where you can bring this G3 and G2 parallel. Now this is, as in this figure, this is not parallel. And what is the hindrance for these blocks to be parallel? It is a summer. So think in this line to split the adder. I told you a plus b plus c is also equal to a plus c plus b. So there is no problem in interchanging the inputs, and you can split the summer, and this is a case of that. And this question also proves the easiness of SFG. You will be, again, even if it is complex in the block diagram, still in SFG it will take only 2 minutes to arrive at this transfer function. But try to prove that this transfer function is the transfer function of this block diagram by the block reduction technique. Okay. Okay, so here is some practice problems for you, and you are supposed to complete this and post it in Google Classroom. And I will be posting I will not be posting the question. You will be asked to post in an assignment with the heading tutorial 1. Okay, so today itself I will be sending that, and by tomorrow you need to complete this assignment. Now you have the first problem for you, that is quite simple. So you have an R of S and a summer, then you have a G1, again another summer, G2, another summer, G3 and G4. Then you have a feedback, 3 feedback path. One is a unity feedback, and be careful that you don't have any connection between this one and this one. Okay, these 2 feedbacks are 2 different things, no connection between. So this is directly connected to the summer, so this is equal to, since there is no gain, so the unity, this gain is equal to -1, right? Now similarly, in this feedback you have a H2 and this is having H1. So you are asked to find out the transfer function of the block diagram. Okay, transfer function of the block diagram by block reduction technique. So it's very important that you should be careful in when you read the question papers and while doing the exams, that sometimes the question may be asked in this way: find the transfer function using block reduction technique. So you cannot use SFG. Now you can use SFG for verifying your answer. Now if it is not specified in the question, just to find out the transfer function, you can simply use SFG. No problem, you need to get the full credit for that. But if the question is to find out using block reduction technique, you need to resort to that block reduction technique, and you won't be getting credits if you just do SFG, because we know that while we have done 2 problems from that, we've seen that SFG is very, very simple. Okay, now the thing is that this is a very simple thing. You can just reduce this okay, by just an analysis. Okay, you will feel that too. And what you can do is, when you change this point to this point, you can combine this, and altogether this becomes a canonical form. You can convert this, and you can do that by yourself. Just go through that. So it's quite simple. Now that's your first problem, and the second problem is quite a different problem. That is, in this, you are to ask to find out the you are to find out the overall transfer function of the system. Now this is the first time you are being asked like this. Overall, overall means you need to sum up the effect. So here in this problem, this is the first problem that we are doing, and this comes under the multi-input system, right? And what are the multi-inputs? There are, one is R of S, other is D of S. Okay, now assume that this is a linear system. So you have already studied in your signals and systems regarding linear time invariant system, and in a linear system it obeys superposition principle. What is the superposition principle? Now, okay, by making one of the input to 0, find out the response of the other input, and vice versa, and take the sum of those. So that's the concept. So what you need to do is, if to find out the overall transfer function, first of all you consider d of s to 0. Now what happens when d of s to 0? When d of s is 0, this summer has no meaning. That means you can consider this as a simple straight line. And then it's going to be a single input block diagram, right? Now after that, make r of s to 0. Now once when you make r of s to 0, this summer has no meaning. That means you can just directly connect, you have only the effect. So still again you have received a block diagram in one input. So from this you will be able to get what? From this you will be able to get C of s by D of s, and from this you will be able to get C of s by R of s, right? These are the two transfer function, and when you take the sum of this, you will get the overall transfer function. After this, you can verify your problem by doing this step, right? D of s, put D of s to 0, you will get a block diagram. Convert that block diagram to signal flow graph. Similarly, convert the block diagram corresponding to R of s is to 0 into a signal flow graph, and verify your answers by this. So all these steps need to be shown in your assignment, that is block reduction technique. So the question is, by block reduction and verify your answers with SFG. That is also part of this question. So you may just do it, and I will give you the instruction in the Google Classroom. You need to submit under the heading. I will be posting a topic called as assignment, whose name will be tutorial 1. Okay, fine. Okay, so that brings the end of our module 1, and you have some more things in the module 1, which is linear and non-linear control system, time invariant versus time varying systems. All these things we have studied under signals and systems. Okay, I'll be giving you notes on this, and I'll be asking one of you to take a class on this topic, that is the types of feedback control system, linear versus non-linear control system, time invariant versus time varying systems. Okay, so